Does anybody want to spend a few minutes talking about the homework? Yeah. So, I mean, what questions did people have, or what? Any observations that people want to share about difficulties they had that they hadn't worked out?
Didn't work it out, but I couldn't get the Ricker to work in TMB.
Cool. Yeah.
Also, I was wondering, how long do you expect these homeworks will take us?
I mean, I like a lot of things, it can vary widely from student to student.
Right.
I mean, I think for a 5, I was told that I should make it a 5 credit hour class instead of a 4. And a 5 credit, I think officially a 5 credit hour class is supposed to take 15 hours of homework per week, 11-week class, so 165 hours, 4 homeworks being a big piece of that. 4 homeworks in the project. I don't know, each homework could take 10 hours, I don't know, at least a day, And, I think that's just an average, so, for people that are, having difficulty, it can take a bit of time. Unfortunately, I don't think there's any real shortcut around, learning a new language and learning a new kind of, for a lot of us are not, don't have come in with experience with maximum likelihood mixed effects modeling background. So, both of those new skills I think can take a lot of time. In terms of the Ricker, what do you mean you didn't manage to get working? So online we kind of went through some different, was it a compile?
It was an optimization issue.
In during the inner optimizer or the outer?
I think it was the outer optimizer.
Yeah, and so.
No, it was the inner, I'm sorry.
Okay, and so for the, maybe we can talk, if you have an inner optimizer error, yeah, and I remember that from what you said online. If you have an inner optimizer error, what are the kind of things that it's worth looking at? Anybody have ideas?
So maybe one of the random effects isn't doing something?
Yeah, so it's usually some issue with the Laplace, the Laplace approximation. But if it ran the first time you did the inner optimizer, it works. But then sometime during the outer optimizer, it gets to a place where the inner optimizer stops working. Is that what happened, or did the inner optimizer work the first time or not?
So everything worked for the Gompertz.
But if you build the Ricker and then run the obj_fun $obj part the first time, like I usually have before you do the minimizer, did that work the first time? Okay, so if the inner optimizer never works, so there's one that's like the inner optimizer works the first time and breaks during the outer optimizer, and to debug that, I recommend printing all of your outer optimizer fixed effects vectors to a file, finding what vector of fixed effects broke it, and then turning off, inspecting with that set of fixed effects what's specifically the problem with the random effects. If it breaks the first time, it's likely to be a bigger issue, become more structural issue. And so anybody have any tricks for the inner, debugging the inner optimizer?
For that model specifically, I was getting an issue because I had set the starting value of k to be 0, and then I realized that was calling NA values. And so I just set everything in log space and then reran it, and it seemed to work. But
Totally, right. So the Ricker is, unlike the Gompertz, you have to make sure that R, K is positive, and really R has to be positive too for it to make any sense. So that's one difference. Any other tricks for if you have the inner optimizer not working that people have thought about? I would say the main trick is just not making anything random, so putting that random input to make AD_fun null, and that means all the fixed effects and the RAM effects are all treated as fixed effects. And then you can do a gradient function evaluation and make sure that all of the RAM effects have a non-zero gradient. That's the easiest way to break a Laplace approximation, is having a 0 gradient for any of the things you're treating as random effects. You could then use the map to turn off a bunch of the fixed effects, all of the fixed effects, and just tap the random effects. And then basically hand code what the inner optimizer is doing, like set up a nonlinear minimizer, optimize that, and then calculate the Hessian using the optim_hess function. And check what the Hessian looks like. So you can kind of hand code all of the inner optimizer. And just see where it breaks down. Does it break down when it's searching, or does it break down when it's trying to do the Hessian calculation? And that would allow you to see if like one of the random effects is getting off into La La Land, or if it's has no function, the gradient is equal to 0 given the fixed effects. Did anybody have trouble with the, and we can talk more after class today too. I'm just kind of hitting on the general strategy. Did anybody have any sensitivity to the fixed effects values they started with, besides the sort of bounding?
In the Ricker model, in my simulations, I don't know exactly what happened because I just had a third of them or so just fail. So I ended up using I fit the Ricker to the observed data to get some reasonable starting values, plug those in, and then everything sort of worked.
Totally. So that's a clever way to do it, is to, like, if we're fitting a state space model, and so you can always fit sort of like a process error or measurement error model version of the same model, like fit the Ricker in a simpler way, pull out those parameter estimates and use that as a starting value. And that's sort of like a way to make sure that you start close enough that it doesn't get into La La Land. Any thoughts theoretically about why the Ricker might have this sort of sensitivity to initial values? There's sort of a concept here that's worth noting.
Isn't it chaotic
Yeah,
at certain points?
exactly. So if the R parameter of the Ricker exceeds a critical threshold, and I forget what that value is, it's like 2 or 3 or something, then the dynamics are chaotic. And what does that mean?
Like you just bounce up and down. You get it.
Yeah, exactly. So the formal definition is that it's like with Lyapunov exponents, where like a small, an asymptotically small perturbation, like a machine rounding error of like 1 to the trillionth, 1 to the 10 to the negative 16, which is sort of the rounding error on a machine using a double slope precision, that error will accumulate as a function of time given the updating equations of the Ricker when it's chaotic. And the implication that has is that if you have a small change in the state in time t, it causes a huge change in the predicted state in time t plus 10. And so the conditional, the kind of joint likelihood function ends up being hugely multimodal, is essentially what it means. And so the Laplace approximation breaks down, and it also ends up just being hugely numerically unstable in the inner optimizer. And so the net effect of this is just that any kind of simple implementation of a state space model will kind of fall over for chaotic dynamics, whether it's Bayesian or maximum likelihood. And there's some emulators and approximate Bayesian computation that gets around this. But that's sort of one general principle that this homework can run into, is that you've got to be especially careful if you've got nonlinear dynamics, like the Gompertz is linear, but if you have a nonlinear model, your state space model can be much harder to fit, particularly if it becomes chaotic.
Yeah, I noticed when you were specifying the random effects on I think it was last week's for the multivariate Kalman. Right?
Yeah.
When you were specifying the random effects, when you used REML, you added like the variance and like Yeah, you changed the parameters, which were random, and I was wondering what.
Yeah. Have we talked about, I think we had just one slide about REML, but I probably should have put it in again. Does anybody remember what we talked about with REML? As a starting point?
It's sort of a way to get, there's sort of bias on your estimates of variance, and Rebel's a way to get around that.
Yeah, so there's this like, the correction term that Fisher and Pearson fought over, of like that you take the squared, is an estimate of the variance, the squared deviations divided by n, or is it divided by n minus 1, where we all use the n minus 1 bias correction, where you kind of correct for the mean that's being estimated, this sort of estimated degree of freedom. And so that's sort of the bias. A maximum likelihood estimator uses essentially is equivalent to doing the 1 over n, whereas we know an unbiased estimator is 1 over n minus 1. Unbiased estimator for the variance. This also brings up a larger point, which is that if you try to estimate the standard deviation, which is the variance the square root of the variance, using that n minus 1 bias correction, is no longer unbiased, because suddenly you have a nonlinear transformation, and that requires a different bias correction. But setting that aside.
This question online. So how do you constrain the parameters in TMB?
So you can constrain the fixed effects using the NLM, using the lower and upper arguments to NLM I and B, or if you're using the TMB helper optimize, it also has arguments lower and upper that by default are negative infinity to infinity. But there's no way to constrain by hand the random effect values. The random effects are always assumed to go from negative infinity.
Can you turn off this?
Yeah.
Like,
Remind me how.
it's on the left side of the door, it's the right hand switch.
Check and maybe turn on the other.
That's fine.
Let's see, okay, so REML. So REML deals with this bias, this n minus 1 bias correction term when estimating variance. And what I say in the slide, and even forget what week it was in, is just that you can do sort of a generalization of REML for nonlinear mixed effects models where you treat all of the non-variance fixed effects as if they're random with a flat prior. So I would still call them fixed effects, but I integrate across them. I put them into that vector that's being treated as random. And so like you saw in the code, to do REML, it's just a matter of taking all of the fixed effects names and putting them into that character vector that I'm calling random so that they get integrated across.
Okay.
But you can't integrate across any of the variance parameters. So it's just like the intercept, like in the Ricker model, it would be, K and whatever I call it, alpha or beta or R. But the variance of the measurement process and the variance of the state, process errors still have to be fixed.
Can you go back to how to constrain, is it the fixed effects, or is it you can constrain specific parameters?
Yeah, so for the Ricker, I think the best general solution is actually what John said. We have kind of take a reduced model and fit it, and then use those as starting values is probably a good approach across a bunch of different problems. But, and sometimes that's called like sculpting, where you take optimization in several steps. That's what ADMB land calls it. I don't know if there's a general statistical term But in terms of the Ricker specifically, there's this chaotic dynamics if R exceeds some, let's call it 2.8, I don't know what the value is. If it exceeds that, it becomes chaotic, and kind of theoretically, we think that the model, our Laplace approximation will fall over past that value, and so you might constrain, you could either estimate R to constrain from 0 to 2.8, or you could estimate log R constrained from negative infinity to the log of 2.8. And what that would look like in terms of this lower upper syntax is like you'd have NLM line B, start equals obj par, objective equals obj fun, gradient equals obj ger, lower equals some like, say the first one is K, and then the second one is R, and the third one is some other parameter, and upper equals K again, which we want unconstrained, and then R, and some other parameter. It would just be it would be a vector with the same order as the order of parameters in the obj par, and then just kind of arbitrarily ordering in this arbitrary. Any other responses to the homework?
What was the expected way of how to forecast from the first 31 time steps to like 32 through 36? Because I think I generated basically 1,000 draws with the final values of that first sort of model fit being used as the starting like point for those 5 time series. Sort of tried to take the variance into it, but I think that's not the correct way to do it.
Yeah, so I bet the problem with that would be that you probably don't propagate the variance of the parameter estimates that are being used, the parameter estimates, like if you have the Gopher, it's alpha and beta.
Yeah.
Or maybe you're using like alpha and rho or whatever parameterization you're using. So, the way I was sort of imagining people would do it would be similar to how we did it in the lab last week, where we do these forecasts here where we've got data for year 1 through 1 through 100, and then we're forecasting 101 through 120. And these variance bars seem to be behaving in a plausible way. And how did we do it in that homework? Or in that exercise?
Sorry, what did you say?
How, in this exercise lab the last week, how is it that we implemented? How would you describe how we implemented this forecast in the R and C++ code?
By removing the last 5 years of data, and then you generate the estimated value for the last 5 years.
Totally.
And then you see how well the fit is between the actual true values and the estimated values. You can compare the two.
Totally.
And you can use the standard error that's output by TMV to generate those forecast confidence.
Totally. And so, so the way that I recommend doing it, as with any code, there's a lot of ways to get there, but I think the cleanest code that propagates variance both about the forecast process as well as the parameter estimates of that forecasting process is to code the states for both your estimated years, your years with data, and your years without data as just a set of random effects. And then just have no data for the forecasted years. So in one sense, a forecasted year is just identical to a fitted year, except just with no data.
So you can have 32 years of data and then 36 years of like how long you're going to estimate for.
Exactly.
Okay.
Yeah, And the way we did that in the code for the lab last week was just to have in this example, 36 years of data, 36 years of states, but have a bunch of NA values for years 32 to 36 and have the code set up to skip any year with an NA. In the data, probability of data evaluation loop. Does that make sense, or do you want to look at the code for that?
Yeah, that makes sense.
It was supposed to be like this, but I ended up getting like almost the exact same predictions for both models. And I thought it was like something I didn't code up right, but it looked like the parameters were different. Like alpha and rho was different than my K and R. But like they looked like almost exactly the same, with like out to like a decimal place or two difference. And
That's funny.
I just could not figure out why.
Yeah, I forget what values. I mean, I'm sure that the Ricker and the Gomperis can look pretty similar over a certain range of values. So and I forget what values you used in the homework. So
I definitely got different, like, mean predictions going forward.
In the forecast part.
Yeah.
Did you set something as a random effect?
The state,
Okay.
like FD actor, D underscore T or whatever, log ET. I don't know. I think I did something wrong, but I really not sure.
well, and then I wanted to remind, or I wanted to remember to announce that I put up like a homework 1 solution. If you go to the GitHub repo, there's now a homework solution, which is sort of for people that are curious to look. And I, as always with homework, I kind of took the least ambitious sort of approach. So instead of doing the Tweety, I just did a delta inverse Gaussian or something, which is kind of the smallest additional thing I could think of to add. But for people that are interested, I mean, I think, that the script is, to my view, quite short, and it kind of illustrates how you can kind of have pretty clean code, although people hate that I don't do text wrapping on my code. I don't think I'm grading anybody on coding style, but as the responses to homework 1 indicated, I am, trying to get, as the homework said, I want the R and the CPP so that I can try to run people's code. And like in this homework 1, I tried to get part 1 running on my machine, and then if people were having trouble or getting results that didn't make sense, I was trying to dig into the code a little bit more. So I, for instance, on this homework, I don't know if I'll get into the details of people getting different results for the same, but if I have time, maybe I'll look into it a bit. Okay, any other kind of business before we get going today?
What do you want for the project?
Yeah, so the project is kind of officially assigned today. I mean, this is the first sort of, so next Tuesday by the beginning of class is due the first product of this project, which is basically a short description of what the data set, what the model. And then I think later we have a required turned in thing, having you simulate data from the process that from the model you're envisioning. And then eventually we've got a written and an oral component of the project. So in terms of like appropriate projects, I think I can be convinced of a lot of things, but kind of as a starting point, something that includes the concepts from this class. So, has some spatially referenced data and some spatial variation and some process and some changes over time. So some spatiotemporal data set and some process model would be ideal. For people that are really convinced they only want to do a time series or a spatial thing with no time series. I'm happy to talk about that. Is anybody having trouble well, maybe after class people can talk with me if you're having trouble coming up with an idea.
Kind of want to do,
What's that?
our Chelsea Woods thing.
Yeah, do you?
It sounds super cool, like thinking about it.
Cool, okay. I think she'd be excited to hear that. I hadn't told her yet that nobody was.
I mean, if I could get a publication out of it, that seems.
Well, okay, that's her goal.
Yeah.
I mean, yeah.
Super.
Well, let's talk after class about it. So today, this week really is sort of, well, it's the first where we actually talk about spatial models explicitly, and it's also basically where we get, as I've been promising, this is sort of the class where we start talking about sort of efficient versus not, separable versus non-separable implementations of the same model. So that's the goal by the end of this lecture. But before we get there, we've kind of already been doing 1D processes with these time series models. So we've been doing, a first order autoregressive model across time and then a multivariate version of that. And so you could just re-index time as space and you would have a spatial model, a smoother on space, that's perhaps replicated across time. So, we've already got a lot of the core concepts. But I guess I'm used to sort of people, ecologists talking about time as discrete time. So we index processes, like in fisheries, a lot of times we index processes in discrete time by year because there's some seasonal processes that we don't want to dive into the kind of within year, differences in temperature, causing differences in growth, and we have, seasonal spawners that we don't want to look at pulses in recruitment. So we just aggregate to year and we ignore seasonality. In public health models, as far as I can tell, they're doing really like the global burden of disease. It seems like it's doing tiny, like 2 kilometer by 2 kilometer global maps, but how much within year detail are they building it, or is it still kind of annual time step?
Annual.
Some teams are doing like daily now, but that's definitely not the work.
Yeah, so I mean, I think that a lot of people kind of start out spatiotemporal models with this sort of discrete time, by which I mean time is integer valued, whereas space might be continuous valued. And so that's why I haven't been, that's why I'm kind of framing it the way I have so far. And so if you kind of get into these 1D spatial models in continuous space, you can start thinking about coastlines or distance away from an experiment. Like Jim Clark, who's like one of the people I learned a lot of like early stats ecology from, his textbook. He's a tree ecologist, and so he does all these leaf traps, pollen count, studies where you put something, little pots, increasing distances away from a tree and see how far their reproductive output can disperse. So those are all kind of continuous space. And as soon as you start thinking about continuous space, you kind of want to start thinking about random functions. So, instead of, previously we had talked about random variables or a vector of random variables, which maybe we call a random vector. But their continuous generalization is a random function, and a random function, we're always dealing with multivariate, with normally distributed random effects. That's sort of the place people always start. And so the random function extension of a normal distribution is called a Gaussian process. Gaussian for the, a normal is also called a Gaussian distribution. And so so this random, this Gaussian process has, on the left-hand side, it generates a random function, epsilon, and I'm using script notation for a function to distinguish from a vector. It would be lowercase bold, or a matrix would be uppercase bold, or whatever. And the Gaussian process on the right-hand side has input as two functions. One of them is the mean function, and one's the covariance function. And so the mean function, in this case, is a zero function, which means that it's a zero-centered Gaussian process everywhere. The expectation, if you resample the process at a single point, is 0. And the covariance function, if you give it two locations, S1 and S2, S for space, then that represents the covariance between repeated draws of this random function at those evaluated at those locations. And a random function has sort of the same intuition, I think, as a random variable, random vector, except it's sort of, if you want a differentiable function, you're going to have sort of 3 moments instead of 2. So a random variable has a mean and a variance, and a random, kind of minimally, like if it's normally distributed, that's sufficient. But a Gaussian process has sort of 3 concepts that are sufficient. It has a mean, a variance, and a decorrelation distance. So in this case, I'm calling the decorrelation distance the scale, essentially. And if you generate, on the left-hand side, here's multiple realizations or lines from this random function Gaussian process that has a standard deviation of 0.5, or on the right-hand side, a standard deviation of 1, where these, if you look at a given point, the variance is greater, than the one on the left-hand side, but, the standard deviation is twice as big. And then the scale, on the top hand row, a scale of 10, means that if you go about 10 units, they're kind of decorrelated. The random function decorrelates at about distance 10. Whereas a scale of 25 means that the squiggles are much slower to decorrelate. The kind of valleys and hills are about 2.5 times further apart than the bottom row than the top row. And then, of course, the third moment is the mean, but I'm assuming these are all 0 mean already. So, does anybody want to talk about kind of Gaussian processes and random functions more on a conceptual level at this point? I just want to get people thinking about sort of continuous extensions of the kind of random effects that we've already talked about.
What exactly do you mean by scale? Is that distance between points, or?
It's just another way of describing that decorrelation distance. And I think scale, I think these are generated using the random fields package in R. I forget what I used actually, but scale is oftentimes defined as sort of twice the range, and range is often defined as the distance at which you reach a 10% correlation. So it's, the exact definition doesn't really matter, except that if the scale gets larger, the decorrelation distance gets, proportionally larger. And it's sort of, I like the term scale sometimes because it's sort of, obviously the decorrelation distance defines sort of the scale of the process. If you want to think ecologically about how far you have to go, if you want independent samples, or if you want to get outside local environmental conditions or whatever, all those processes sort of are proportional to the value scale. So we can come back to the Gaussian process that I got into Gaussian processes because, well, probably like anybody from kind of a roundabout route, and I was interested in sort of model misspecification. So we were just talking about Ricker. So we do a lot of these surplus production functions in kind of classical fisheries, and so there's like an argument about whether, fish kind of look like have a black line, a surplus production curve that looks like this, or it's more left skewed, or maybe it's compensatory where surplus production doesn't go up and then it goes up. And there's a long literature on arguing about the shape of that. And we did a paper looking at like a semi-parametric model of surplus production where you'd have a parametric production function and then you'd have a Gaussian process on top of that. So you'd say your production is the sum of a parametric part and a Gaussian process part. And as you have data in the red line, if you have enough data, it kind of learns how much your specified production function differs from the true production function. And it kind of, the Gaussian process soaks up that model misspecification error. So the red line is able to pick up the true curve kind of in a state-space model if you have enough data, whereas the blue line is what you get if you just specify a parametric production function. And it ends up being horribly biased because of this model misspecification bias. So that's why I got interested in Gaussian processes originally. I think it's sort of a general, it's one of those things that all of us should have in our toolbox of stuff that we're used to seeing and hopefully working with. Is my claim. Does anybody want to talk more about this? It's just sort of a example. Yeah.
What would be the difference between using the Gaussian process in the 1D case versus the like random effects, like a random effect or something like that?
Yeah. In practice, computationally, I don't think anybody ever actually works directly with the Gaussian process, and they just think about it theoretically, and then they evaluate it at a fixed set of points, in which case it reduces back to that random vector implementation. The way I think about it with Gaussian process is that it's kind of just a theoretical way of interpreting a bunch of random effects typically. Inferentially, it's useful because you could say, say you have data for years 0, 20, 40, 60, 80, and 100, 6 data points within this function. You could say, what's the predicted value at any location within that, and then you have a vector of 7 locations, 0 through 100 plus the location of the new data. It would have no data associated with it, just like how we did with forecasts before. And and that would give you the predicted variance at any possible location, and you could theoretically change that value anywhere continuously and map out what's the predicted function given your data.
So at those discrete points, you would estimate, say, just like we've been doing, like the sort of the deviations, saying that those are maybe normally distributed or whatever. But then instead of just stopping there and saying, oh, okay, well, around our observations, we have this variance. You're saying, and then that variance actually comes from this covariance function of some Gaussian process. So then you can sort of use those as actual estimates of C.
Exactly.
Interpolate.
Exactly. And that's sort of a way, like geostatisticians used to fit a model with your data, and then they'd have another projection matrix to project to new locations, and then they'd have this challenge of propagating the estimation variance, just like the problem Nat had of propagating estimation variance if you don't use the delta method to do the whole thing. And so, just like the response to Nat, one easy workaround that kind of generally works is to just treat the whole thing as an estimation problem, but where you're missing data at some locations. And that will give you the same answer as the old geostatistical way that used to be much harder to code up. Yeah, and I'm just paraphrasing what you already said. I mean, the benefit is that if you think about it as a function, you can think about predicting it at any continuous location where you don't have data. So instead of like the global burden of disease stuff being a grid where you're predicting I mean, I always found it, I mean, and so I think other people say this too, that it's silly to say that, oh, you're predicting HIV risk, you know, at every 2 by 2 kilometer cell, and then putting the number of cells on the globe out as sort of like an index of how complicated the model is. But it's a flashy big number. But like you could say, well, you know, if you think about space as a function, you could predict HIV risk at any point, and the number of points is the power, you know, it's like the power, what is it, power functions of infinity. It's, which is like the number, you know, the number of complex numbers, I think. So, I mean, which is way bigger than the whatever number they sell the Gates Foundation for the number of predictions they're doing. So, I mean, you know, once you're thinking about functions, you can think about infinite number of predicted locations and actually start computing at any resolution. And that's, you know, that's how like your monitor renders an image that works regardless of the resolution of your monitor. Is it's, you know, or how Adobe Acrobat works is that it encodes a series of functions, and then you've got a GPU on your machine that renders those functions with the number of evaluation points, meaning the number of pixels, you know, given you're playing a first-person shooter, given the direction you're looking, and just use a bunch of linear algebra to render that function with the pixels that you need.
I was gonna ask about, I guess, like the lines that we're looking at here. So it seems, tell me if I'm wrong, each one is more or less like a draw from sort of this like multivariate random normal thing that's like it's a Gaussian process. Like I guess it's like in my head it's like a multivariate normal of functions.
Yeah, totally.
Okay. So when you're like fitting a model, I guess like in the same way that like maximum likelihood estimation would evaluate data given some parameter values for like a normal distribution or something, or is it evaluating each of these like function types? Like I guess like how does it go from like parameters you have to like these lines, like, and then looking at your data?
Yeah, so again, I mean, this is sort of what we're talking around. So like, in the background, you want to say that you've got a function, but in reality, you only ever query the function at a set of points. So like, if you rendered it, you know, you're limited by the pixels on this projector probably. And so you know, to get a perfect representation of it on a monitor, you'd only need the pixel DPI to figure out how many evaluations you need. You know, if somebody zooms in on a global burden of disease map, you know, you re-render the resolution you want to evaluate the function at. But so in the background, computationally, all it's doing is a finite set of locations and treating it as multivariate normal. But inferentially, you're still treating it as a function. And a function can be evaluated in an infinite set of points, and that's why it has sort of a different name, sort of an infinite generalization of a multivariate normal, which is only defined for a finite set of locations. Well, I want to make sure we get to this sort of other kind of, I mean, this is sort of major concept 1, and there's sort of major concept 2 is the separability. So let's pretend we've got a coastline, you know, and this is again my like California bite, you know, Southern California where the coastline goes inward, where you've got this observation function G, and you've got mu is a function, a mean function that you're evaluating at a fixed set of 8 points, and you have counts S at each location S. So the ways that we can do this, you know, you can block them, or you have a random effect for north versus south, and then another nested random effect for site or something. You could do equal distance autoregression, where you kind of sniff each location to kind of be equal distance from one another, and do the same kind of Kalman filter, like equal distance in time, treat time, you know, space is time, and do what we already know how to do. Or we could do unequal distance autoregression, and that's what we'll talk about in the lab tomorrow, Thursday. So sticking with equal distance autoregression, we just kind of snip it, you know, snap it down to this equal distances. and assume a first order autoregressive process for the so we've got this X is a design matrix, beta is a set of fixed effects. So if X is a Gaussian process, let's see, if epsilon is a Gaussian process and X is defined for every possible location, if this X is a covariant function, then you can interpret the mu as a function, and then you can interpret, density as a random function. But in this case, we're gonna stick with the equal distances autoregression, and so we won't try to interpolate the mean points. And then, this is just the sort of, what we saw as a first order autoregressive process. So if you look at the correlation between points, the correlation at distance 0 is 1, and then the correlation goes down. The correlation for distance 1 is rho, and for distance 2 is rho squared and rho cubed, and so forth. So that's just sort of, an exponentially decreasing function. And so if you start kind of, pencil and paper kind of, scribbling down properties of this, you can see that the variance across, the variance from s equals 0 to s equals infinity, so as distance goes to infinity, as long as rho is between -1 and 1, it's a convergent series, and a conversion power series, if you look that up online, the formula for the variance would be this. The correlation we already saw for distances is rho to the d. We saw that on that plot, and so we can say that the total covariance is just the correlation times the marginal variance, which is down here. So we can generate the whole covariance matrix for this process. And it looks like that bottom equation. And so, we've already kind of talked about this in the time series context where, if this is the variance, then as rho goes to 1. As rho goes to 1, it becomes a random walk, and the marginal variance goes to infinity. It stops being stationary, which is why this formula stops working. There's no stationary variance, or the variance goes up infinitely with distance. And so this is a representation of the covariance that we wrote down before, where this is the correlation matrix, and this is the kind of piece, the marginal variance of it. And that will be sigma, and we can write this equation down. Here's the second way we could write the equation down. The first way we wrote it down this way, where we've got the same observation likelihood, we've got the same linear predictor, but this is using this sort of like recursive formula for defining the probability of epsilon t plus 1 at s plus 1 given epsilon at s. This is the second way we can do it, where we just have the multivariate normal distribution for the density of all the random effects jointly. So that's the same model, but instead of a recursive formula, using a single formula for all random effects. And we could evaluate that. If you look on Wikipedia, as we've said before, the formula for the multivariate normal probability density function looks like this. And the formula for the multivariate normal probability density function only ever deals with the variance squared, or the variance inverted, which we've been calling the precision matrix, or Q. And Q, by the way, people started using for the term quadratic. And that's because this looks like a quadratic thing, where you've got a vector and this again. So there's sort of like this vector of random effects squared. That's the term quadratic. to evaluate the multivariate normal, you need to figure out the inverse of the covariance, and you need to calculate the determinant of the inverse of covariance. And those are really computationally challenging operations. And so a third way we could do that is to code up the inverse covariance directly. And the inverse covariance is sometimes called like the partial covariance matrix. And it represents the impact of element I on element J after partialing out the effect of all other variables. And so without any attempt at a proof, I'm just gonna posit that the covariance looks like this, and we can confirm that later, that if we invert this, we get the same formula that we derived before. This is the formula for a conditionally autoregressive model or a CAR model that you could look up in a spatial stats textbook. So a third way we could do this formula is just hand coding the Q matrix like this. And the fourth way is that TME has some built-in, built-in functions for spatiotemporal models. So the fourth way is just using this built-in function that TME has. And so now we're going to look at TME code that implements all four of these different methods that we've kind of breezed through. And the goal is to show that, first of all four of the methods give the same answer, or, almost the exact same answer, but that they behave fairly differently in terms of speed and memory. And the reason for that is that they differ in terms of separability. So we talked about this already a little bit. Separability arises from the need to do this multivariate integral to calculate the marginal likelihood, and how in some cases we can break that integral into a series of smaller integrals, and how in the Laplace approximation separability is there's a one-to-one mapping of that integral definition of separability to this other definition of separability, which is about the structure of the Hessian matrix that's used in the Laplace approximation. So if you can break the Hessian into a series of subblocks that are all zero between one another, that would be equivalent to a model that you could break into independent integrals. Does anybody want to talk more about separability? We've talked a little bit about it, but I know we haven't really used it in detail. So.
Can you just go back to the last slide really quick?
Yeah.
So when you're integrating with respect to epsilon, what is the dimension?
Yeah, I'm being really lazy about my integral notation.
I just want to drive it home because that seems like the key thing is that that's a really big integral.
Yeah, and so sometimes when I write this out these days, I have DEV bold to indicate that, it's integrating across.
That would be like every single one of them.
It would be yeah, exactly. And I know that there's a lot of people who've taken more math than me care a lot more about the notation of how to write out those integrals, multivariate, multidimensional integrals. But yeah, the point is that it's an integral. It's a series. The best way to write it out would be if this is linked 10 as 10 different nested integrals where you have to integrate the inner one and then you have to integrate the second one for every value that you previously integrated for the other one, and then so on. And so if you've got 10 random effects, it's sort of a 10-dimensional multivariate integral. But eventually we want to, on my laptop, we all as a class will be in theory able to make models with 100,000 sort of, locations, combinations of location and time and species. So, 100,000 dimensional integral is just kind of impossible. I mean, it's impossible to think about, I think. So it's, going back to our example of 10, I think we've already seen a few, but can people think of a case where we've got a 10 random effects and they can all be blocked out into an independent integral? Or what's some of the separable models, kind of thinking about it this way, that we've looked at in this class so far?
When we did that Kalman filter, we broke out that multivariate normal into
Totally.
separate little normals, 0, 1 normals.
Totally, yeah, exactly. So that, in that case, each of those was a two-dimensional integral, and that resulted in a Hessian that was kind of this. They call it tri-diagonal because all of the elements, so there's only 3 elements in Hessian that matter. But without getting into kind of that complicated, there's a few kind of block-structured Hessians we've seen that correspond to sort of separable integrals. One of them is the homework 1, where we had, homework 2, where we had we had a random effect for each site, and then we had multiple observations per site. And so in this case, you could do the integral for all of the observations at a given site. Well, you could do the integral for each site, and you'd have to, that would be the sum across all observations at a given site and the random effect for a given site. And you could do the integral for each site independently of every other site. And that makes sense because, all of the observations are independent for every site. There's no observations that sum across sites or anything. I don't know if that's a helpful tangent or not. Does anybody else want to take a crack at sort of talking about this?
I just have a question about how, like in the TMB code, I think a couple of times you said, oh, this line here is desirable because it's separable, and I don't know if I have a sense for what actually about the code makes it separable versus like an analogous way to code it up it would be.
Totally, and that's exactly the point.
Oh.
So that's, thank you for that. So if we look at the code, and is this zoomed in enough? You can see this, okay. So, oh, this is speed force. So, at the top is just the code to generate those random Gaussian processes that we looked at originally. And then the plot for how to visualize the autocorrelation function. So this is all the stuff that we've already looked at, just plotting code. Here's a math check on that claim I made that the, so if we've got our autocorrelation of 0.5, we've got a marginal variance of 4, and we've got locations 1 through 10, we can calculate the distance as well, there's a bunch of ways. There's actually a function called dist in R that would do this, but I just kind of wanted to write it out. So dist is the distance between locations. A location in itself has a distance 0 all the way from site 1 to site 10 has a distance of 9. And so if we write out the covariance, using that formula, it looks like this. And the inverse of that covariance inverted looks like this. And then we can also write out the precision matrix analytically using the formula that I just kind of posited. And the only difference is this cell, the bottom right and the top left cell, where if you actually calculate the Q as the inverse of the covariance, it's a little smaller than the Q that I worked out. And that's because I'm cheating. The CAR formula is a little bit more complicated than the way I presented it. But that'll essentially be kind of a boundary effect where, I guess I would have to invert the Q2 to see what effect it actually has. Where, yeah, at the boundary, my inverse covariance is slightly less variable than the actual covariance would be. So in some of these solutions, you end up with equivalencies that work up to a boundary effect. I then simulate data from 100 locations and 3 observations per site. So CSI is a matrix of 100 sites, 3 observations per site. It's a Poisson distributed generalized linear mixed model with a random effect epsilon S that follows this autocorrelated process across space. Does anybody want to look at the code for simulating that for a second? Or like one way to do it is just to generate the epsilon by generating the first value and then using a recursive formula for epsilon S simulated based on epsilon S minus 1. And then doing a loop through all the sites and all the years as this Poisson log linked linear predictor. And then finally, what we're going to compile, I'll just do the R side all in one piece, and then I'll look at the C++ file. So we have a single C++ file that has the parameters, which has the 100 epsilon S. It has beta 0 log sigma squared and logit rho. Why am I doing logit rho?
Because they can go from -1 to 1.
Yeah, I mean, in this case, I'm just constraining it to go from 0 to 1. I don't want to deal with rho getting greater than 1. Because, as we've kind of talked about, that results in a non-stationary process, and that will complicate the math for some of these solutions and not others. So, is that?
Yeah. Is there any benefit for doing the logit versus putting the bounds on when we're running in TMB?
For a lot of cases, no. That TMB, almost any optimizer assumes all the parameters are on the same scale, meaning that the gradient is about the same for a 0.01 move of any fixed effect. And so if you don't work in the logit scale, as you get from 0.99 to 0.999, it can cause a huge shift in the log likelihood for some models. And so, whereas if you use logit, it's more likely to be approximately stable across all values. So I think that's why people found it internally rather than on the optimizer side. So here I'm just going to run the same code over and over again, but I'm changing options back from 0 to 1 to 2 to 3. And as you can see in the notes, the first one is the stochastic process. The 0 is this one, where I sweep through the random effects as using this recursive formula. Option 1 is this hand coding the precision matrix using the formula that we looked at, or you would look up in the future, I guess, and I just posited it. Option 2 is you hand coding a multivariate normal density function. And option 3 is this pre-built function in TMB that we'll see in a second. So, using the tricks that you've all been encouraged to learn, you can put all those in the same C++ function. Let's get some code here where I'm linking that. So all of them run, let's see, cbind part 0, part 1, part 2, part 3. So they all give roughly identical answers. Technically, par 2 and par 3 are identical, whereas par 0 and par 1 differ. Well, in locate space, they differ in rho a good bit in this simulation replicate. But the marginal variance of par 0 and par 2 are very similar. Well, this is only off by a little bit from that one. So par 1, the precision matrix is a little bit different because the boundary effects we already started talking about, how I kind of cheated in my hand coding a bit because I didn't want to bother to look at the exact equation, including the boundary conditions. But, you know, all of them are giving very similar answers. But if you compare timing, well, these took almost identical. So the internal TMP and the hand-coded precision matrix both took 0.1 seconds, whereas the hand-coding the multivariate normal density function took 1 second, and the recursive formula took a little bit longer than these two options. So there's about an order, you know, a 10-fold increase in time that this one took. And if you don't know anything, you know, if you're not used to seeing this, it's probably not immediately obvious why that would be. So the next step is always, you know, really, if you build mixed effects models, sort of the first thing to look at is almost always plot the separability. So again, I'm using package IMLA to plot separability because it has this kind of somewhat optimized plotting function for it. So version 3, version 2, version 1, and version 0. So they all look basically identical. They all have this sort of negatives on the off diagonal and positives on the diagonal for the Hessian matrix. And then 3 of the 4 models have this big expanse of white that indicates that those are identically equal to 0. So it detected separability for 3 of these 4 models. Whereas this one, it's got a bunch of gray boxes where gray is equal to 0. So version 2 is the one where it didn't successfully detect separability. And version 2, sure enough, is the one that took 10 times longer. And so, you know, looking at this more, we can actually start looking at the structure of, you know, these H's is what I got from this obj and SP Hess function that we've looked at before in class briefly. I think I found this function actually after some people had left one of these classes. Do people remember seeing this function? How about raise your hand if you remember seeing the SP Hess function used before? Well, yeah, so this obj and SP Hess random equals true is a function for extracting TMB's internal representation of the Hessian matrix that it uses in the Laplace approximation. And if we just so it fits on the screen, if we plot out the first 6x6 submatrix of the Hessian from the version 0, we can see that it has this sparse matrix, DSC matrix class, which I don't know what that means, but it says it's a sparse matrix. And in R, sparse matrices are displayed on your screen as a matrix by having a dot in any element that's known to be identically equal to 0. And so you can kind of get this hint that version 0 detected, you know, sparseness, and so internally it's representing the Hessian used in the inner optimizer in this sparse way where it knows that it's always going to be 0 except for that tri-diagonal structure. The same thing holds for H1. But then H2, the one that took a lot longer, has the same values for the diagonal, but it's got a bunch of zeros, and it's Well, it's funny, it's still saying it's a sparse matrix, but it's just incorrectly putting these as zeros. So I don't know what's up with that really, but so I guess it's detecting that it's sparse, that it's doing it wrong or something. I mean, it's just doing it inefficiently, where the version 2 that took 10 times longer is tracking a bunch of zeros in this Hessian that are not actually needed. And H3 again is detecting sparseness. So, so that's sort of what we already saw in those images, but kind of seen in matrix form. Where, the punchline is that version 2 didn't detect sparseness, and so it took about 10 times faster. So are people following kind of that level so far? We haven't looked at the C++ code at all yet. Well, let's kind of keep going, and I think that this is sort of, as I said at the beginning of the class, I think weeks 1 and 2 are, kind of harder for some people. Weeks 3 and 4, we were trying to consolidate concepts for weeks 1 and 2, really. And then weeks 5 and 6 suddenly are a bunch of new kind of material here. So I'm expecting this will take repetition and seeing a couple times for it to really connect with a lot of people. So the R code, so that the C++ code, which unfortunately we only have 10 minutes left to look at, but we can take up later. Well, there's this DMV norm. So I wanted to make a multivariate normal density function that's similar to the DMV norm on the R side that people are maybe used to using. Well, except with the difference that it takes the precision matrix Q. So anytime I use Q, it indicates a precision matrix. And I don't really want to get into the code too much about, I could probably do this more efficiently, but at the time I didn't know. I was building this originally without wanting to use the determinant function built into TMP, so I kind of rebuilt it my own way, and the trace function and so forth. So DMV norm is a way of evaluating a multivariate normal from a precision matrix. And then in the main block of code, there's this options vac that we've seen where we specify the method. There's this matrix of data, there's the 3 parameters we already looked at. And then there's this vector of random effects epsilon. We extract the size of the vector. We define the joint negative log likelihood and keep track of 2 different components, JNLL comp, dot comp, underscore comp meaning components of the joint negative log likelihood, in case I wanted to look at that.
Wait, what is that?
It's just my kind of programming style where sometimes in a big model, that joint negative log likelihood will always, for a mixed model, has at a minimum, it has the probability of data given the fixed and random effects. And it has the probability of the random effects. And so for debugging purposes, sometimes I want to keep track of both of those separately so that I can look and compare them with some outside calculation. And for big models, you've got a bunch of random effects. And so I've just gotten in the habit of having a vector called JNLL comp for components of the joint negative log likelihood, and I keep track of all of them separately and report it out. So it's just it's a programming style thing. So in this case, joint negative, the second slot, or JNLL comp 1, is the log probability of the random effects. It's the negative log probability of the random effects. So actually, I can back that. So that the first way of implementing this is basically the same way we simulated it, where we take we calculate the probability of the first random effect from some distribution, and then we've got a recursive equation for the probability of each random effect given the last one. So like epsilon s given epsilon s minus 1. So we kind of sweep upstream to downstream through a set of ordered random effects recursively and, kind of like Grant was talking about. That's the way we also did all the time series models. So this should look familiar. The second way is hand coding Q sub SS, where I say SS just to keep track of the dimensions of that matrix. And this is just a formula that I gave without trying to prove it. And then using the hand-coded multivariate normal density function that I built. Here is using hand-coding a covariance function using the formula that we kind of derived in class. And then here's the first time we'll see this MV norm in caps lock. So in the long term, we're going to see a lot of we're going to end up using these functions once we are confident that they're working the way we understand. So options 2 and 3 both use these caps locked functions that are in namespace density. And so you can use that namespace by just declaring using namespace density. And that's C++ equivalent to like saying library MVT norm or whatever. So that it knows that you want to use some of the functions from that namespace in your later code. So in this case, MV norm and caps lock is part of that namespace density, and you kind of have a key that it's a non-standard function because it's in caps lock. And MV norm, we can look at it later, it's a function where you give it the covariance, and then it returns a function, and then you can call that without saving it. You can just call it on another function, which is the vector of random effects. And that returns the negative log likelihood. So unlike in R, one easy way to mix yourself up is that these namespace density functions return the negative log likelihood. And so instead of saying minus equals, you have to say plus equals. So that's, hopefully people caught that. We'll see it again, so we can talk about it again. And then finally, the built-in function in TMB doesn't even require hand coding the covariance. You can just, well, this is sort of a slightly complicated way of saying this, but the AR1 row function returns a standard normal for a first order autoregressive process with autocorrelation row. And because it's standard normal, it doesn't have the covariance that we want. And so then you can use this function scale and rescale it to have the covariance we want. Or technically, you rescale it with the standard deviation that you want. And so this is the marginal standard deviation of this process that we looked at also in one of the slides. We're kind of running out of time, so I'm kind of speeding up a little bit here and we'll cover it again on Thursday. But so we generate a first order autoregressive process, a function that would return the negative log likelihood for a standard normal first order autoregressive process. We then rescale it to have a new standard deviation, where the new standard deviation is this that we derived. And then we hand that function this vector epsilon sub s. And that returns the negative log likelihood. Not the log likelihood, but the negative log likelihood that you have to add to your joint negative log likelihood. So those are the 4 different ways to code this. And then we've just got, we finish it with this loop through the probability of the data given the random effects and the fixed effects, just like we've been doing for weeks. So, so do people remember which of these versions was the slowest?
1.
The second one.
Yeah, I think it was called, yeah.
It was 3 in the R code and it's 2 in.
Exactly, I think it was called H2 for version 2, yeah. And it's, so this one And it runs slower, we saw, because it didn't correctly detect separability. It was tracking a bunch of elements of the Hessian matrix internally that were not needed. And just looking at it, I'm not exactly sure why this one didn't detect sparseness. I think that this multivariate normal is just not designed to really do that. MV norm just assumes this covariance is dense, so not sparse anywhere. I think the bigger interesting question is sort of why, or like how it detected that this one's sparse and this one's sparse and the bottom one's sparse. It kind of makes sense that this one is using a bunch of hand-coded special functions in T of B. So of course it's most plausible, not knowing anything, that it would detect sparseness for this one. But if we looked at the timing, it actually, that option 3 that uses all the hand-coded stuff is not quite as fast as option 1, where we hand-coded the precision matrix ourselves. So, basically, I don't want to get too far into it right now, but the point is that separability in TMB is not something that you put into the C++ file. It's a property of the model. It's a property of the parameterization you chose to have, where it's able to detect it if it's there. And it's really a question of coming up with a parameterization, a series of parameters where the partial correlation of random effects is 0 for some of them.
It seemed though they were 0 in that model.
Well, exactly.
In all of these models.
Yeah, the partial correlation was 0 for all of them, and it only correctly detected it for 3 of the 4. Is that what you're saying?
Yeah, so it's not just the model. The model itself has to be in the separable format, but then also TMB has to be able to
detect
that.
Yeah, so it's probably a good idea, even if you kind of are familiar with your model, to look at that SP Hess output, look at the internal representation of the Hessian matrix and just plot it using that image function from INLA, and just look at it and kind of think about whether it matches your expectations. Like, I think we did that first for the Kalman filter, which was that equally spaced time intervals, and we saw that it was tridiagonal because the partial correlation of time t and time t plus 2 is 0, conditional on the value in time t plus 1.
Because could we tell sort of from the specification on the slide, the one with the 4, where you have the 4 ways to code this?
Yeah.
I mean, from that.
From that, you kind of think all of them would be able to detect sparseness because they're all pretty similar. So if we wanted, we could come up on the lab. During the lab time, we could come up with we can intentionally try to come up with another parameterization that is not separable and show that would presumably take as long to run as this one where it didn't detect sparseness.
To help just with my understanding of all this, can you give an example of when the model itself just can't be coded to be separable? Like when I guess the zeros are not always necessarily going to be 0, or like in
Yeah.
object.
Well, so I forget when I was gonna get into it. There's almost every state-space model has 2 kind of intuitive parameterizations, and I think if you just don't know anything about separability, people kind of 50-50 end up with states as treating the innovations as random effects or treating the states as random effects. And so we're already 4 minutes over time, so maybe we should talk about this later because it's kind of an important concept.
Sure.
Okay, so let's call it for today. And pick it up again on Thursday. like I said, I think that, really, well, first of all, there's only one homework left. And then it's all about the project. So, by the end of the 7th week, you'll have we'll have gotten through all the spatiotemporal, kind of basic spatiotemporal material. And so really, by the end of this week, or certainly by the end of next week, I'm hoping that people have sort of at least a working kind of intuition about kind of separability and how to code stuff efficiently. So if by the end of next Tuesday, you're still pretty confused about it, I think that's when maybe, it's worth talking individually or whatever. Okay, thanks everyone. People online good?